to listen to the former speaker. I think it was an excellent introduction, not only to exfoliation, but to oxide growth in general. And I have always been a good friend of oxide growth because that was actually the basic for my understanding what happened in a boiler, especially what happened in the superheater section of the boiler. I introduced myself in a very, very simple form nearly 40 years ago, this oxide dating model, because I thought that was a good tool to understand what really happened when we had some of these superheater failures. And thanks to that, and thanks to investigation in superheater failures, I think that we climb up the ladder of knowledge of what is actually going on in a superheater. And we also try to put this on paper and in models to operate this knowledge better inside, but also outside, because I think the main problem we actually are facing is superheater is a very dominating problem in modern boiler design and modern boiler operation. And even though I think too little of the already gained knowledge have come to the boiler manufacturers and are used by the boiler manufacturers. Too many boiler manufacturers are using some rules for constructing their heat surfaces, and these good old thumb rules have been used for more than 50 years, so they must be very good. But even though we continue to have a boiler with a very, very bad heat pickup, and sometimes it's that bad that you feel that the boiler manufacturer, the boiler constructor, had very little knowledge what happened in his own boiler. Well, apart from that, I will go into the subject I have concentrated about, and this in the beginning will be mainly about exfoliation and what exfoliation can cause. Of course, we know that superheater reheater failures, especially in USC boilers, are well-known phenomena and unfortunately still very common. And we know that two predominating failure types are seen. Overheating, either due to incorrect construction or due to oxide exfoliation and blockage. We began to utilize austenitic material in the beginning of the 90s because we elevated steam parameters, and we exceeded the 540 centigrades, which was a limit for only using ferritic materials, and going to 650 first and then later to 600 centigrades, we had to use austenitic materials. Before that time, we had very little problem with exfoliation. In our fully ferritic constructed boilers, we now and then could have problem with the inlet to the turbine due to blockages of relatively thick oxide scales coming from the steam line or from the large stage of superheater due to exfoliation after being in operation for far more than 100,000 hours. But these problems was easily solved. You just have to shut down the unit and take out the sieves, clean them, and then operate for further 1,000 hours. No problem. And here we are talking about boilers who made rather cyclic operation, and also boilers which were equipped with relatively low alloyed materials compared with the actual temperature, steam temperature. So when we took samples out of the superheaters and even the part of the reheater pipe system, we had thicknesses far about 0.5 millimeter, something up to 1 millimeter in oxide. And then I think it's fair that now and then you have a little spoliation. But we could catch all these things in the sieves, and we never saw erosion problem from oxide in the high pressure part of the turbine. Erosion in our turbine is normally associated to the low pressure part due to water droplets compensation. Well, but introducing this fancy USC technology, we had to look into the possibility of exfoliation. And even we have no experience from our own plants, we had very good friends, especially in Britain, who told us many years before that they have been using a lot of austenitic in their boilers, and they please pay attention to exfoliation. It's something which can give you problem. So we did our very best, and the requirement for the superheater, austenitic superheater materials we set up was actually that we should have a material which will never exceed a total thickness of oxide of 150 micron in the full design life. And secondly, we also have this corrosion resistant, less than 1 millimeter for 100,000 hours. And of course, we should have the mechanical properties so we didn't overstep the creep rupture strength. The materials we in those days was looking into was material, I would say the group of the old-fashioned, relatively low chromium materials, especially those made in Germany on the nomination 4910. But then we also look into new fancy materials. There was the well-known 347, but in the Sumitomo version, fine-grained version, that should be a better material due to oxide formation. We also looked into Super 304. That was a bit premature for being directly used in our boiler. And we looked into these two very expensive material where you have extremely good oxidation, especially oxidation data, especially for HR3C, but also very, very high creep rupture strengths. But that was actually not our target. Creep rupture data or mechanical strength for these two materials would be sufficient for our boiler constructions. We built first a boiler, we were commissioned in 1992, SBR Unit 3. It was halfway to the USC steam parameter. It was only 260 bar, 565 centigrades, and it was commissioned in 1992. But then we were planning these two units, which were the first ultra supercritical units in Europe. And what I'm going to tell now is a failure which occur in the SBR unit and the two ultra supercritical units, and which could have occurred in this unit. This is just a plain supercritical unit, but only operating at 540. But it has a lot of austenitic materials in the superheater because of a very, very bad superheater construction, which led from the very beginning, after only 1 year operation, to an extensive replacement of good X20 material to austenitic material to overcome an intensive overheating. Well, let's look into the different problems we had. First, this is some example of exfoliation taking place in the boiler region, and especially this one you should realize. This is what happened at SBR unit. I'm coming back to detail, but here you see this is exfoliated material found just for 1 meter of superheater tube, and this is exfoliated material coming out of the whole tube length. And here you have a Deutschmark. In those days that was a well-known coin. Unfortunately, we don't have it today. Maybe we should.
The euro is shrinking.
Yeah. The euro is getting smaller. Yes, indeed. Yeah. But okay, please put this into your mind, because what happened? Yes, this beautiful boiler construction, which was commissioned in 1992, did a very good job. But after 7 years in operation, maybe only 6 years in operation, 6 years in operation, in 1998, we had to make a hydraulic testing. It was required by the authority, not because the boiler had any problems. We had to make a hydraulic test. So we did during a shutdown and general overhaul. And when we made this hydraulic testing, we filled up the boiler from the bottom and came up to the outlet superheater and filled it up this way and up to the outlet box. And when we have drained or filled it up completely and taken out the air, the test was conducted, and we drained the boiler opposite way, and then we put it into service. And very few hours after being in service, we had the first failures coming here. And this final superheater is made partly using the French 9-chrome material EM12. It was mandatory to use that material. We would have chosen X20, but the French boiler manufacturer want EM12, okay? And the remaining is made of plain 347, coarse grained. But we have failures here. To cut it short, as I said to you, we found this amount of oxide per meter in some of the tubes, and we found all this in the whole length of tube where we have the problems. And by making some calculation and rough calculation, we found there was something tricky in this case, and finally we came to the conclusion that, okay, after 6 years in operation, all the austenitic part had exfoliated or in a condition for exfoliation. When you fill up the boiler with water, you will rinse all the surfaces from all the austenitic tubing here from exfoliable oxide and bring it into the outlet header. And then it's settled. And when you drain the boiler, only those tubes which are ending up in the bottom of the header is exposed with all the exfoliated material. And that it was. We made an intensive work to find and control all tubes coming out from the bottom or leading up to the bottom. And thanks to a proper arrangement and good luck, we were able to detect all tubes which have been affected and replace them if they were overheated, and then later have a troubleless service. So this is what happened in this case. And just to show you some interesting pictures, this is typical example of samples cut of the material. The EM12 has a wonderful double layer oxide, and here you see the chrome image. You only have chrome here. The top layer is pure iron oxide, and here you have the iron image. You have the same image as top. Here you see a non-exfoliated sample of TP347. It's one of the coldest samples of, I haven't seen the lowest steam temperature. And you see again a double layer chrome image. You miss the top, and here you have the top. And here you see what most of the samples showed, the TP347 fully exfoliated. There was only the bottom layer, only this layer was remaining here. The rest was exfoliated. The next example, let me drop that in first time. The next example was one of our two ultra supercritical plants operating the double reheat, 290 bar, 580, 580, 580. It was commissioned in 1998, but less than 1 year after, or nearly one year after operation, we had a problem with the control system. Some quick guy or fancy guy, he did something with the regulation system, and everything was shut down. Everything in the boiler. The boiler was full operation, except the feed water pumps. And they were still running. And as everything was shut down, nobody could see it. But the man in the cellar, he recognized the problem, and he took the main stop of the feed water pump just before the water was coming to the outlet of the boiler. That was a real thermal shocking event. And it wasn't good, of course. And our main concern those days was actually would we have some thermal fatigue problems or damages in the main outlet and so on. We made careful analysis and said, well, this outlet, well, might be able to stand for such a treatment 5 times. So okay, 1 time is enough. We will never do it again. So just bring the boiler into operation. But then very soon after we began operation with this boiler, we had a failure. And we had some more failures. This particular superheater section, that's superheater section number 1, the first stage, should originally have been fully made of fine-grained 347. But you know, these economical guys who are managing companies and so on, and they found it was a little bit more expensive using fine-grained than coarse-grained, and we have a long discussion, and then I was put under pressure, and then from the original information about heat flux, we considered that it was such a good idea to keep down the investment cost. The first part of the boiler could be made by 347. And what I want to have shown you here, we made actually this calculation, and it shows that if you use fine-grained 347, you will have, over the entire life, I said entire life was 200,000 hours, you will be below or come up to something like 50 micron for a full surface. Whereas if you use coarse-grained, you will definitely come above 150 after 100,000 hours. In this particular case, we were not about that number of service hours, and I think we had an excuse. This exfoliation was happening under very severe and very specific circumstances. No one will make such a thermal shock normally. Well, second example. Oh, that's just wrong. Excuse me. Where do I have the last? Something had happened. I have some more examples. Oh, they have been dropped. Sorry. Well, then I have to. Well, something unexpected did happen with my slides. Hey, come on. Oh. Okay. Well, Nordjylland Unit 3 is just the same type of boiler as Skærbækværket number 3. It was commissioned also in 1998, and he did 4 or 5 years operation, and then after a long summer overhaul where they have to look for different things, he commissioned the plant once again, and we had failures just the same place as we have seen at Skærbæk. And now we began to worry because the example at Esbjergværket was something special with the geometry. The example with the exfoliation of Skærbæk was something with thermal shock. This time we were looking into a failure occurring after normal operation. Also here we were very lucky to identify those tubes which were affected by exfoliation, and we could make quick repair and get rid of it. But then we have to think how to avoid these exfoliation problems in the future in a more substantial way, because we have to live with fine-grained and coarse-grained material, and we must accept that we have some coarse-grained material which during normal operation develop that much magnetite during only 5 years operation that it could lead to a failure. Then we had a third example. I think it dropped out of my presentation. It was this Stutzerberget plant, where we normally would consider a plant just using ferritic materials, but due to this improper superheater construction, they had to bring in a certain amount of X8. Well, in this case, we had to replace some of this material, and unfortunately they did replace it with with coarse-grained material again, and after some years in operation, we, for some or other reason, somebody find out that they have a blockage. But we found this blockage before startup of the plant, and thanks to X-ray, and it is a pending superheater. Thanks to X-ray, we could find all the blocked bends, and we cut them out, we cleaned them, and we put the boiler in operation. So no problem. So you say, here we have the four problems. We have Esbjergværket that was due to hydraulic testing. We had Skjærværket that was due to thermal shock due to malfunction of the control system. Nordjyllandsværket that was due to normal operation, not so good. And this one was due to normal operation, but using a material which will grow oxide too quickly. And you see where we have the problem and have a severe exfoliation, except this thermal shock condition. We have the coarse-grained material with a inner thickness of about 70 micrometer, 70 micrometer, and here 70 micrometer. And that seems to be, in my opinion, fitting very well with this general statement, 150 micrometer, the total thickness. Then you should expect exfoliation. Okay. Then, how can we handle exfoliation on the existing plant? And how can we live with it? We think that to live with it is to develop a test procedure to remove exfoliated material, steam blowing, and be sure that we can measure the oxide or pre-calculate the thickness of the oxide, so we are very well aware what happened, where happened, and when happened things. And secondly, of course, we can improve our additional tools, so we can be better off if some blockage should happen, and we have to analyze the individual tubes. We don't hope we come to this situation. And thirdly, we should go for improved material. But if we look into this operating procedure, we know very well that some German chemical plants have been in operation for many decades, operating at temperature up to 650 centigrades. And this power plant, they are equipped with very strong and mechanical reliable austenitic materials, but it's all material which generate a lot of oxide, and it's all material which will exfoliate. And I have seen samples cut out of these boilers, and they have been in operation with no problem. I have seen samples from these boilers, and truly, they are completely exfoliated. They only consist of the inner oxide layer, the chromic spinel layer. There is no thick, or there's only very thin iron oxide layer on the top. So the reason for that is that they have been able to constantly get rid of all material as soon as it could exfoliate. And if you do it constantly, during service maybe, or during startup, you are getting away with the problem. I don't think that they have put special attention to this problem, because they just haven't seen it, and their operation mode have just been fit for fight to get rid of this material. In our case, we were not fit for fight. We have seen that in some cases, even we're not talking about thermal shock and things like that, we had the problem. So we developed a modified startup procedure where we make a purging 3 times of the superheater and reheater to get rid of the exfoliated material which probably has been formed during shutdown, because most probably the exfoliation takes place when you go from a hot condition to cold condition, because then your outer tube is shrinking due to the very extensive thermal expansion of the austenitic material, but the ferritic, the oxide, which has a more ferritic nature with respect to thermal expansion, will stay, and then you will have the exfoliation. So when you cool down your boiler, you exfoliate, and when you start up the boiler, you have problem with exfoliated material. So we make this steam purging, and we run the boiler up to with closed outlet valve, main valve, up to approximately 165 bar, and then we open quickly the high pressure bypass and reheater bypass and blow down to the condenser for 5 minutes. And here you see a typical curve for the first blow. We go from 165 bar down to 90 bar, and then we blow once again, and then third time, and then we go in operation. And you see also what happened. This iron measurement have been made very careful, because making iron measurement in steam is difficult. You need a real isokinetic sampling, and that we have. And that means you need to take out a large amount of steam. You need to cool it down in a cooler, where the cooler is constructed in such a way that you have in the cooler. And then we take a part stream of this condensed steam, fully isokinetic taking out sample, and put it through a corrosion product monitor. And then we allow this, that is just a filtration, and we filtrate for 1 minute or so, and then we can make an average estimate of the iron oxide. And this curve here consists normally of 3 measurements. And you see definitely that the first purging, you are up in the region of several milligram iron. And then you come down to something like 100 micrograms. And when we come to the third purge, you start about something 150, 200, 150 microgram, and you come down to something far below 10 micrograms. And here are the same measurement made in the reheat. And here you have the first purging that goes from 50 bar to 30 bar, and the second purging is from 50 bar to 30 bar. And you see in the reheater section, we are coming down to close to 10 microgram. Doing this and introducing that since 2004, we have had no problem with any of our boilers. And we also see the steam quality with respect to iron reach levels below what we call action level 1. It means concentration far below 10 ppb during normal service. And I'm sure that using this procedure, we will constantly purge out exfoliated material and get rid of the problem. Secondly, we were looking into improved materials, and if we want to do something better, we should look into this scheme. And if you want to get rid of this problem or to live with this problem, you should choose a material which make less exfoliable materials. And if you take the normal 17 chromium or 16 chromium material, you will have a heavy build-up of oxide, and you will have a rather thick top layer which will exfoliate. If you have something between 17 and 20 chromium, it will be a little better, but not good enough in my opinion. If you go for either even a higher chromium content or fine-grained material at 18% chromium, or sharp-peen material also at 18 chromium, you will come much better off. You will have very thin layer, which also will exfoliate, but now we are talking about less quantity. And of course, if you go above 22 chromium, you will nearly have nothing. But that is very expensive material. If you go for the fine-grained sharp-peen material below 20% chromium, it's a fair solution. And that's definitely what we want to do. And then finally, I just want to show you what kind of evidence we have behind this investigation and conclusions we are coming up with. At Esbjergværket Unit 3, we have been operating with this kind of test superheater. We have had 3 of these one-tube superheaters, test superheaters installed in the boiler, and these individual tube consist of various pieces of various materials. Meaning, we have an inlet here, we have normally an inlet temperature about 500 centigrades, and then we will expose to the first coil, normally ferritic materials. And then in the final coils, we will go up to even nickel alloys, nickel-based alloys. The first test we run for, in total 7 years, the first coil was taken out, or the first superheater was taken out 1 year after, and the second one 3 years after, and the last one was operating for 7 years. And we had an outlet temperature 620. Then we have improved model, we have another test where we had outlet 635, and we have one 700 centigrades, and we have one, that was the last one taken out last year, 720. The unique thing by this test superheater, which we constructed together with former EVT Stein Industry and now part of Alstom boiler, was that we have not only a control valve which control the flow, so we have just the right outlet temperature we want, but we also have a steam flow measurement. So we can measure exactly the steam running through this installation, meaning that we can measure the heat flux and heat pickup by every coil, because we have externally here measurement of steam and metal temperature here. So we know exactly the condition of this test rig, which you normally don't do when you see in most experiment shown in literature from cervix exposed material in boilers. You know nothing about the real test condition. This led to very precise here you see the test condition. Here you have the test superheater on top of the final superheater installed in the boiler, and here you have them in the workshop after operation. What we were able to calculate, and this is part of our fancy superheater calculation program, which also are used to justify a new construction, how well it functions or not. This is what happened actually in every superheater material or tube. You have a steam temperature, and then you have, due to the internal heat transfer coefficient, which is definitely depending on the flow, and an increase of temperature, which is the heat flux divided by the internal heat transfer coefficient. And in a test superheater, this can be a heavy jump. And in real superheaters, it can also, especially as a reheater, it can be something more than 30 centigrades, which is about this. Then you have an increase of the magnetite layer, and there you have, if you want to simulate the surface, you have to simulate hour by hour, increasing this thickness, increasing this insulation effect, increasing the oxidation constant, because here we take the temperature for the oxidation constant, that's in this position 603 centigrades, and this goes up and the oxidation goes faster. So the total insulation effect, including the internal heat flux, will increase the metal temperature for oxidation, the mid-wall temperature, which could be used for calculating the creep rupture strength, and the surface temperature, which should be related to an eventual corrosion, fireside corrosion. And using such a test facility, you get the right figures, otherwise you don't. Here's some example from samples from this test condition, and I just want to show you one here at the end of my speech. Here you have two samples of one of normal 347 and fine grain 347, and they have been exposed close to each other for 23,000 hours at a metal temperature of 620. They have just the same temperature, and here you see the difference between a fine grain structure and a coarse grain structure. Here you have up to something like 55 micron spinel, chromic spinel. Here you have up to 15. And in average maybe 30 here, only 6 here. And here you hardly see the top because it has already exfoliated. here you see a very even top of this iron-rich oxide. This is this kind of information you get from such a test rig, and I could give another speech about paper about that. So when I come to the conclusion, I think we have to accept that austenitic materials is required for superheater in USC boilers. But we have to accept that we have exfoliation problems, and we have to accept that we should use materials which don't develop too much exfoliating material. And then we should try to minimize the exfoliation problems by knowing the construction, knowing exactly what happened, choose the right material, and then finally make a good start-up procedure so we can purge away that material which even the very best precautions